All right, essentially the big thing that you should have done, or maybe you haven't done yet in 3.5, is connect some of what you know about the graphs and what you know about the values and exact values and stuff, and create a graph for sine y equals sine x. You should start with the points that you know. If you're trying to draw y equals sine x, you should know that this starts at 0. It goes up to 1 here at pi over 2. If you're working with scales, horizontal scales here that are in terms of pi, if this is pi here, and you want to find pi over 2, well, halfway, right? There's 6 squares, so 3 of them. If there's 6 squares, that's how many squares pi is. 1 square is pi over 6. I know it's going to be up at 1 there, and back down there. Just kind of by unit circle definition, and then down at -1, and back up there. If you're trying to draw it, use that framework for kind of getting the curve right, and just fill in the rest of it after. That's enough to kind of get the curve right if you drew it on top of there. You can put some other points that you know if you know your exact values. The other things you know is hopefully that sine of pi over 6. What was sine of pi over 6 from those exact value triangles? Sine of pi over 6, 30 degrees. It was a half, right? So if you want to get the shape right, you could put something roughly at a half there, and I'm not going to be perfect with it here, but because that's enough to get it right. It's about as close as I can get, I think. I'm not quite on there, but more or less something like that. If you were drawing it accurately, okay, all of those points are going to fit, and it's going to look like that. If you really wanted to get it right, you could do the other one, which was pi over 3. What was sine of pi over 3? Square root of something over something or whatever? Yeah, square root of 3 over 2. Or if you work that out as a decimal, it's about 0.87. So it's somewhere in there. That's all you're doing in... I'm not putting them on the exact right points here, but that's all you're doing in that tutorial. You're just making connections with what you already know, and you can keep going here if you wanted to. I'm off a little bit, but that's close enough. Okay, and so on. So that's enough to get the shape accurate. If I actually put the function in now, it should match more or less with those points. Okay. One cycle of that pattern is, I mean, the thing is periodic. Okay, there's a graph of sine. I was almost right with most of those. But one cycle of the graph is from there to there, right? This is 0, and it goes up, back down, and back up to 0 in 2 pi, or 360 degrees. If you keep going with it, it just keeps going. If I start moving this over to the right, the pattern just keeps going forever, right? However big your angle is, because it's based on rotating around, right? If you have a pattern that happens by something rotating around, the pattern just keeps happening, okay? If you get on a Ferris wheel and you're the rider and you start in the middle, I don't know why you'd start in the middle, you'd probably start at the bottom, but you get on and you go up and down, and if it keeps going around, that cycle just keeps going, same pattern keeps going. It would go up to the top, down to the bottom, back up to the top. Okay, it's periodic. If we change the scale here and squished it down like this, you see it just keeps going there. Okay, but to draw the graph, you're going to look at one section of the pattern, and to keep in mind as you do that it starts at 0 and ends at 0 after one cycle. This thing, one cycle, is one complete piece of the pattern. One cycle takes 2 pi. That's its period. Okay, the period is how long one cycle takes there. Something you talk about is how high or low it is. The distance from the center to the top or center to the bottom, okay, is the amplitude. You may have heard that word before. Whether you've done this or not, maybe at the end you can do something for yourself here. There's some words at the end here. The period you talk about, both of them. Okay, period of both sine x and cos x is 2 pi. It's the horizontal distance for one cycle, okay? I don't know what you want. Well, I can't remember what I was thinking we put on here. It's a periodic function. It's not just that there's a piece of the graph and it doesn't repeat. It's repetitive, right? It's got a repetitive pattern. What's the domain of this function? Just keeps going forever left and right? So it's all real numbers. What's the range? Yeah, 1 to -1, right? Sine ratios, we could put it like this. Or you could put y if you want. Right, sine is between 1 and -1, or again, you could write it with the y. Probably better. In either case, it's that. How are the graphs the same and how are the graphs different? If we go back to this. For sine, it starts there, goes up, down, back up again. For cosine, it starts at the top, and then this happens. But after that, it's just the same pattern, right? This thing just keeps going here. Okay, for sine. Oops, I'm not doing a good job of writing it, but... Okay, the rest of this pattern is the same as now. If I wanted to get it right, I would put some of the other points in there because I think I'm missing tremendously here. If you're trying to draw that shape, I want you to notice that in the middle here, it's at an angle. You don't draw it with half circles. So you don't draw it like this. Okay, it doesn't go like that. It's not completely vertical in the middle here. That's one extreme. The other extreme is it doesn't look like this. Okay, it's not saw teeth. It's kind of somewhere in between. It crosses at an angle in the middle here, but it's rounded on the top and the bottom. For now, that's probably good enough to understand, I think. But just know that if you wanted to draw it more accurately, you could put some of those other points in. Even though the pattern for one cycle looks quite different, with cosine starting at the top and sine starting in the middle. Once you draw more than one cycle, it's hard to tell the difference between the two other than the point in the cycle that they are. If this was, I don't know, one of the classic applications is something rotating around like a person on a Ferris wheel. If this was a person on the Ferris wheel, these kind of describe almost the same motion other than where they start, right? I don't know how this person got on here if they started at the top. And this Ferris wheel must take them down below ground. But despite all of that, if you have this point here moving along, okay, they're down at the bottom, up at the top. It's the same motion either way. So there's a lot of similarities there. The shape is exactly the same. The range is the same. The period is the same. The only difference is the y-intercept, the starting point. Okay, so if you want to describe that for yourself after, you can comment on how they're the same and how they're different. I don't want us to spend, if you want to go back and, make sure you can draw the nice graph at some point, that would be good. But that's the goal of this, is just to connect the exact values and what you know about the general shape with drawing a nice graph here. It's nothing more than that. Somebody in my other class said, do you have some questions we could actually do? Because it doesn't seem like there's any questions to do in here. And I think that's why some people find this hard, is because there's a lot of concepts, but there's no, okay, now you go and do these kind of things. Like in grade 8, somebody can teach you how to solve 3x plus 5 equals 7x minus 2. Okay, go and solve that. Someone can show you one or two, and then they can say, here's 1,000 of those questions. Go and solve them all. This is not necessarily like that, because it's concepts. This is what the graph of this looks like. This is why it looks like that. This is why the exact values and stuff. We can ask you exact values over and over again if you want, but we're not going to get to actually doing something with this maybe until you start doing transformations of these graphs. If this is your graph of, if you have your basic graph of sine here and it looks something like that, except it doesn't. It looks something like this. not even that, but more or less. We're going to do transformations of that. You're going to compress them this way, you're going to compress them this way, and so on, right? But for now, we're just kind of understanding why they are